So without further ado, I'd like to introduce Bob Button. Bob, thanks for joining us today.
Thank you, Buck. I wanted to thank everybody for attending this presentation. As Buck and Jim mentioned, this is a PDH presentation, so you will get one professional development credit for attending this. And in the end, what I hope you gain from this is the direct comparison between these two products, an induction beam with a drain pan versus a sensible only chilled beam. Hopefully at the end of this, we will see the two products for what they are, the benefits of each, and where they are best applied in our buildings. So made in America for the American market. It appears just to be a slogan. I'm just going to talk about the company for a moment on the first slide, and then the rest of this presentation is fairly void of marketing since it is a PDH presentation. So made in America for the American market. New Climate was the only US-based company producing induction units and chilled beams back in the early 2000s. And so made in America for the American market really meant something, because these guys were engineers from Carrier, executives from Carrier who formed this company, and they really felt it was important to adhere to International Mechanical Building Code that said you had to have a drain pan under a cooling coil or an evaporative coil. So from the very beginning, that is the stance New Climate took. We're going to not only provide liability protection, but what that drain pan is going to do is going to open the door for a multitude of designs that you're not afforded with a sensible only chilled beam. So the presentation hopefully is going to cover just a general knowledge of the product. Nothing here is going to be a deep dive since we only have an hour. So we'll talk about how it works, operation history, and the evolution of the product. Sensible only designs, which is primarily what the European manufacturers have advocated for exclusively. And then the fully condensing designs we're going to talk about, and that's really part of the evolution of this product. And that really happened in the United States. So we'll talk about the challenges of the product, because both sensible only and fully condensing induction units have challenges like every system. I'll show you some system designs and some of the strengths and weaknesses of those designs. If we have time after, I'm happy to show everybody pictures of jobs after the PDH portion of this, and show our selection software, which really captures how these units work and really gives you a very good understanding of their function, the relationship between static pressure and sound and induction rates. So it's really good to see it in real time, making changes and watching the conditions change. And I would encourage people to stick around if they would like to for that. And the history of the product, really, chilled beams are not unique in the way they work. Carrier back in the late 30s, early 40s developed the Carrier 36 series induction unit. They were produced right here in Syracuse, New York, where I'm located, about 3 miles from here. They were a very simple device. You would bring in your primary air or your outside air to this plenum right here. It would pressurize this plenum. Inside that plenum, there's a series of nozzles. So when you introduce that air into the nozzle, through the tip of the nozzle, the air is going to increase in velocity dramatically, creating a differential pressure on each side of your coil. So in this case, it was an under the window unit. So room air was being sucked into the coil, through the coil, going up to the incoming air that we're delivering, and then delivered upward, because this was an under the window unit. And what we're going to find is this exact same design in a different configuration is exactly how modern induction units and chilled beams work today. These were so simple that a thermostat opening and closing a control valve regulated temperature in the space while you had a constant velocity of fresh air, conditioned fresh air coming in to this inlet right here. So these were the earliest designs, I believe patented in the 40s. And you'll notice they had a drain pan. So even on the original design, Willis Carrier had the insight to know that even if this was used as a sensible only device, it will condense at some time in the life of this product. I'll touch on this for a second, but sustainability. These old Carrier units haven't been installed since, I believe, the late 60s, early 70s, because they used almost 2 inches of static pressure to operate. That became unacceptable, in the early 70s. So there's more than 1 million of these still in existence, still working in buildings around the country. So as far as a sustainable system, induction and chill beam systems have the potential to last greater than 50 years. And I would say, as sustainability talk goes, that's pretty good for an HVAC system. The evolution of the product, of course, there was a rebirth in the 90s. The Europeans looked at that Carrier design. They used the exact same principles in it to come up with an ACB. So an active chilled beam right here works the exact same way. They're introducing air into this plenum, it pressurizes the plenum, it passes through a series of nozzles, increases the velocity, and so on. It works the exact same way. The difference is it's been configured into the ceiling, and in this case, they're using a horizontal coil, so they cannot put a drain pan under it. It's being used as a sensible only device. Now, in Northern Europe, where this was developed, they're primarily a hydronic heating market. So they're going to ask this to do very little cooling, and if they do, they're only tempering the air. They used their energy differently. They had milder climates. So when you bring this active chilled beam to the United States, we're going to ask it to do a lot more work, including we're going to design to lower temperatures versus Europe. The box on the left is a passive beam. Basically works on radiation and convection. It has no primary air being delivered to it. I see very few of these in designs in the United States. Sensible only chilled beam operation. And sensible only chilled beams have no drain pan. So when I talk about induction beam versus sensible only chilled beams, what really distinguishes them from each other is a sensible only chilled beam does not have a drain pan, has a horizontal coil, and an induction beam does have a drain pan and has a vertical coil or coils. So sensible only chilled beams with no drain pans. The entering water used for these has to be above the dew point of the space. So generally speaking, you're going to see entering water to the coil anywhere from 57 to 62 degrees. And so that poses a challenge. Since we're using elevated water temperatures for cooling, we have a choice to make. We're going to have to populate the ceiling with a lot of coil surface and or really drive the outside air temperature down to gain as much capacity from the outside air as possible so we don't have to continue to overpopulate the ceiling with coil surface. Since this is a sensible only design, the coil cannot handle any latent conditioning at all. So we're going to deliver that primary air to this box at a very dry, very low grains, very dry, often 55 degrees or under at 41 to 45 grains of moisture per pound in that air. So what we're going to be doing is asking these engineers to buy a custom air handler that is generally going to have two dual wheels. We're really going to have to subcool that air to dry it out. So when we introduce that outside air into the space, it's going to do 100% of the latent work in that space because we do not have a drain pan. So the real benefit of this chilled beam that was developed is through Nozzle Technology, now you only need 0.2 to 0.8 inches of static pressure to drive that same circulation that the old Carrier units required up to 2 inches to do that same work. So the evolution that the Europeans brought to this was really shedding a light on, hey, we can do this with a lot less static pressure. And the main reason, anybody is even considering chilled beams other than the, indoor air quality benefits, which are great, is the fan energy savings. So the fan energy is really what drove this. So if we look at the air handle on the left for our VAV system, that ductwork is sized to move total air in the building. So is the fan motor. So we're going to move every bit of air in that building with a fan motor through ductwork, and we're going to even take air, we're going to do energy recovery, and then we're going to redistribute that air back out into the building. So one of the downsides to this with this current situation is you're going to cross-contaminate building air, room to room, space to space through your HVAC system. Now the air handler on the left for an induction beam system or a chilled beam system is going to be a much smaller footprint, because now we're only going to move the outside air. So that's about 1/3 the total air we're going to move with a fan now. So we have to bring in the same amount of outside air regardless of the system for those occupants. The difference now is we're going to downsize our fan motor by up to 66%, and same with our ductwork, up to 66% smaller than VAV. So now we have the real opportunity for enormous energy savings over the life of the system. And that's what drove this product to the point it's at now. On the piping side, now here's where some of the challenges lie. On the piping side, we're going to have to deliver water to the beams that's above the dew point of the space at all times. And so in order to assure that, we are going to have to mix that water in this loop very tightly. We're going to have to use mixing valves, condensate sensors, sometimes heat exchangers, so that water is always above the dew point of the space. Because we're taking the leaving water from the air handlers, and so we are going to have to mix that depending on time of year. Again, we may have to add heat to that. A lot of control points, and in some places like Miami, there's multiple systems. So redundancy of these systems is not unlikely. Traditional building conditions. So with a sensible only system, one of the challenges is you must design your return conditions at 50% RH. Now that's not me saying, hey, it's not better to design at 55 RH. With a sensible only system, you almost have to design at 50% RH, because if you were going to use 58-degree water for cooling, you would have about a 3-degree buffer away from the dew point of the space. If you were going to use 58-degree water for your standard 75-64 design, your 55 RH design, you would be 24/100ths of a degree away from condensing. So that is why you'll almost 100% of the time see sensible only designs designed with return conditions at 55. And this is to demonstrate that if you were to lose control of the space by 1 wet bulb degree, you are going to condense under that 75-64 design. So typically now we have, say we have a 42-inch coil, and I'm showing you this because every manufacturer has the same coil. It doesn't matter if it's us or somebody else. We take that 42-inch long coil, 5 inches tall, 2 rows deep. We'll put 1.5 GPM of water through it, 120 CFM of air. We're going to produce 1,531 BTUs. So again, that's one of the challenges. We have a 4-foot long coil almost, and we're only producing about 1,500 BTU sensible with it. So we're not condensing. You can see the total and the sensible are the same. But in this scenario to the right, if we lose our wet bulb by 1 degree, say the occupants of the building prop the doors open, there's operable windows, and suppose that the occupants of the space don't understand the system, which they never will. So if they do prop open doors, best case scenario, of course, the condensate sensors react in time, close the cold water valve, and you lose cooling in that space other than the primary air that's being delivered. So that's one of the challenges. It's kind of counterintuitive. The coil senses a load it can't handle, so it shuts off in order to save the building envelope. So that's one of the challenges with the sensible only beam. There's almost always spaces in the building that will be in alarm mode. And again, through controls, they work most of these problems out. Same 1500 BTUs I was showing you a moment ago. It's the same coil run. And this is really just to show you, you're going in at 58 degrees. And one of the challenges is with a sensible only chilled beam, you're coming out at 60, 61. So if you've got a 3 or 4 degree delta T, you're doing pretty good. So a low delta T is something you have to deal with a sensible only chilled beam. And then again, some of the challenges in the United States that we deal with are higher sensible and latent load densities. So we have quite a variation in climates in the United States, as everybody knows. And even the latent load densities, we pack more people in buildings, so compared to Northern Europe. So when we bring this device over, we're going to ask it to do a lot more work, and we're going to have to deliver a lot more air. We traditionally deliver more air to our spaces than the Europeans. We have higher outside latent loads to deal with. We have projects all over, Texas, Houston, Texas, Clemson, South Carolina, where, you have 145 grains of moisture per pound in the air down there during peak season. So we really have to deal with a lot of harsh conditions. Code compliant drain pans required. So when we started, almost 15, 18 years ago selling these, that code existed that said you had to have a drain pan under a cooling or an evaporative coil. So we took it very seriously. Since then, a number of years ago, they have carved out an exception for sensible only projects. If they're not designed to condense now, they do not need a drain pan. And so that requirement doesn't exist if you are going to design sensibly. And some of the other challenges compared to Northern Europe is we are going to design our spaces to lower temperatures. So again, we're asking a sensible only beam to work a little harder in the space. And that code that we adhered to, that 307.2 evaporators and cooling coils, is how we construct our drain pans. So an induction unit, whether it's ours or somebody else's, their drain pan should be constructed as the code requires, since that exception for no drain pan is only for non-condensing systems. So once that system is designed to condense, then you must adhere to each and every one of these criteria for designing the drain pan. So there's also an auxiliary drain pan requirement. So if you are designed to condense, you must have an auxiliary drain pan. So the way that we accomplish that is through a UL 508 water detection device, a float switch. So this float switch goes right on the end of a drain pan, and it meets that requirement. Less expensive than condensate sensors and don't require control points. Very, very good option. Sensible and latent induction beams. So this is where we're going to draw the comparison from a sensible only beam that you must design the outside air to handle 100% of the latent in the space, compared now to a sensible and latent induction beam. So a sensible and latent induction beam now has the ability to share that latent load with the coil, or share that latent load with the air handler. So higher capacity. It's no mystery, if you put 45 or 44 degree water in a coil, you're going to get significantly more capacity than you would have if you put 57 or 58 degree water in that coil. So I'm going to show you just some coil runs that will illustrate just how much additional capacity you get. And not only that, how it changes the design or the potential for the design enormously. So what this is going to do, it's going to give the engineer, instead of being locked in a box and designing one certain way to avoid condensation, what a drain pan does is put a lot of tools back in the toolbox of engineers. And so we'll talk about those designs and even hybrid designs. Noise levels very low. That's one of the benefits of induction beams and chill beams, low sound levels. With induction beams, you are going to have drain pans that meet code. Filters are not required, although I see filters in about 25% of jobs. And some induction units are ETL tested for sound throws and capacities. So induction beams with drain pans, they can look exactly like chilled beams. The only difference is this does have a full drain pan. It has vertical coils rather than horizontal coils, so that they're able to put that drain pan under those vertical coils. It comes to 1 3/4 inch copper female NPT connection where those two drain pans meet. So there is one connection. Other induction beams with drain pans can look like more of a standard diffuser with egg crate return and multi-fin diffuser, 2 foot, 4 foot, 1x4s. So really quite an array of models, all-way blow models, 2x2, 4x4 all-way blows, that 2 of them in a 1,000 square foot classroom, very, very high capacity. And this is to show you the induction beam with drain pans. Now, what can you do with an induction beam with a drain pan that you couldn't do with a sensible only beam? Well, we can start over here with the primary air. So no longer are you required to bring outside air in at very low grains. Now, because we can share that load with the coil. So if you're able to use 42, 44, 45 degree entering water to your coil, you no longer have to bring in outside air and thoroughly dry it out and bring it to the chill beam very cold. So now the goal would be, let's use cold water, bring in air now higher grains, maybe 55 grains at 60 degrees, dry bulb. So the goal now is, since we have all this capacity, we can get more neutral over here and try to become more efficient. We no longer have to try to make up the difference in capacity because we're using warm water for cooling, so we're not having to overpopulate the ceiling with coil surface. Again, 0.2 to 0.8 inches of static. These are very, very quiet. This particular unit has the ability to deliver 475 CFM of outside air to a space by itself, a 3-to-1 mixing rate. So for every 1 CFM we bring into the inlet, we'll induce 3 through the return and discharge 4 into the space. Very, very thorough and effective ventilation. So this is really where the rubber meets the road now, so to speak. So if you had 42 degrees, 42 degree water, that same coil we talked about earlier, 42 inches long, 5 inches high, 2 rows deep. So now instead of producing 1,531 BTUs with that 1.5 GPM, we're producing about 5,000 BTUs. So now you might imagine how much less coil surface we're going to need throughout that building. Or now we have the ability to balance that to our liking more so than with a sensible only beam. So now our delta T, we can look at that as somewhat, we can manipulate that somewhat. So since we have all this capacity now, or even if it was at 44, 45 degrees, we're going to have similar capacities. We can manipulate that delta T sum to the liking of the engineer, within reason, obviously, like everything. So now what we can do, same coil, we can taper back the flow. So now we're at 0.5 GPM, same 42-inch long coil. We're still producing almost 3,500 BTUs versus 1,500 BTUs. So now our delta T goes up to almost 14. So I could show you with our selection program scenarios where I give you an 18 or a 20 degree delta T, or I could show you scenarios where I give you a 10 to 12 degree delta T. So my point is that is just something we have more control of in this type of design than we do in a sensible only design. And I wanted to stop for a second and say this because it does sound like I'm really beating up on sensible only designs. Probably half of our overall projects are sensible only designs. I would say that in the last 5 years, it has been a lot more slanted towards cold water or hybrid designs where they're designing right at 55 degrees, which is right on the edge of condensing. So I wanted to get that out of the way. And they are just different systems, and some of them, depending on the project, one makes more sense than the other. So at 0.5 GPM, we are producing still more than 200% more, and we can manipulate that delta T significantly. So this is where the exponential savings occurs right here. So look at this room on the left, 58-degree loop right here. So we have our four 4-foot units in there, our 42-inch long coils times 4, 1.5 GPM each in those. And that's that 1531 times 4. So we're producing about 6,100 BTUs, 6 gallons a minute in that space. So over to the right, we have 2 units, same coil, but we're at 1/3 the flow with half the units. So we're at 1 GPM in that space. We're still producing almost 7,000 BTUs. So now, if this is a school where there's a corridor or an office building, so you have one corridor that has 10 rooms in that one corridor or down that one corridor. So now you can say, okay, 10 rooms, 10 times 40 units, 10 times 6, 60 gallons a minute and 40 units down that hallway versus 20 units at 10 gallons a minute. So now things look a little different for the piping and the pump sizes, and you can really look at this in more of a global, with a global aspect and say, wow, am I going to be pumping a lot less water around the building? Are my pumps going to be smaller? My pipe's going to be smaller? In addition to, I'm going to need half the number of units potentially. So that's really where the exponential savings occur. And it's not just the cost of the units or the cost to hang that unit. It's the valve packages, it's the insulation, it's the circuit setters, it's the check valves, it's all of the accessories, and it goes on and on and on for twice as many units in that building. On the water side, we talked about, this was the sensible only loop that we talked about. You know, you'll see some form of this on a sensible only job. Well, this mixing valve and the condensate sensors and the booster pump and all this really becomes unnecessary. So if you have a drain pan and you are draining that drain pan, you're no longer required to mix that water because you're not going to have to take the leaving water from the air handler and then mix it tightly so it doesn't, potentially rain in the space. What you're going to do now is eliminate all that. You're going to send cold water to the induction units in parallel now to the air handlers rather than taking the leaving water. And now we know we have an enormous amount more capacity in that building, and we're going to require significantly less coil surface. And or we can deliver warmer, wetter air and let our coil do a significant portion of the latent, which is going to free up a lot of dollars on the custom air handler side. So offices, universities, healthcare labs, these are really places where this product really shines. In New Climate, we've done an enormous amount of work in universities and education, healthcare. That is the PDH portion of the course. I would be happy to answer questions, and at some point I would like to even show some pictures.
All right, so the first question we have is, can this technology be used in retrofitted systems?
Absolutely. Probably at least 50%, maybe even more of our projects are retrofits. And one of the benefits of this system is since we're only delivering the outside air, if you have to put ductwork throughout a building, the ductwork is a lot smaller than a lot of other systems because we are only going to move the outside air. Yes.
Next question is it safe to assume latent beams are deeper than sensible only?
Deeper meaning taller. Yes, depending on the model. I would also say that there are models of induction units that are relatively the same height as sensible only chilled beams with no drain pans. But generally speaking, yes, a little bit.
Okay. What condensate removal strategies are typically used, especially for out in the middle of room units where gravity is difficult?
Okay, that's a good question. I would say depending on your ceiling height, we can give you extension collars that go between the actual unit and the diffuser. Or in some cases, we build that integrally into the unit so the unit is taller, which provides for a higher drain line. So we have equipment that has its drain when it has an extension collar on it, 10.5 inches above the ceiling line. So at an 1/8 inch per foot, you can really get out there pretty good. That said, a lot of times if they don't have the ceiling height, I do see pumps used regularly. And one of the things I could show you with the selection program is how little condensation these things produce. And that's one of the things that always baffled me is these things produce such a small amount of condensation, but we're designing these big, giant, elaborate systems to deal with that little bit of water. So that's why, gravity draining when possible just makes so much sense. And so I would say 85% of our jobs do not have pumps on them. Sometimes the classrooms say they don't have a straight run. They'll take 2 or 3 spaces to one common sump and use one pump. But I do see pumps on every unit sometimes.
Okay. Another question regarding condensate. Being the condensate pan needs to be the lowest point and the chilled beam sits on the ceiling, how does the condensate get out? Is there a pump attached at each chilled beam?
Like I said, generally no, but what I would say is since we adhere to the International Mechanical Building Code that says that you have to build that drain pan so it's internally sloped, to facilitate gravity draining so there's no standing water in it. So every one of our designs, the unit gets hung perfectly level and that slope, that 1/8 inch per foot is built into the drain pan itself. And then again, we can give you extension collars to bring it up higher if you need more gravity draining.
Okay. It seems that the water temperature is much lower, 42 degrees, for this system. Does the chiller capacity increase at all, or is it relatively the same due to the lower flow rates? The chiller operation and first cost could be significant.
Yeah, I guess I should show 44 degree water because, we rarely see 42 in the field, but we see 44, 45 a lot. And I would argue that most of these facilities, K through 12s, universities, hospitals, are already producing that water institutionally. So they're taking advantage of water they're already producing at whatever temperature. And they like the fact they're not having to create a system to mix that and create a whole separate piping loop. Okay. Did I answer the question?
Well, if you didn't answer your question, ask a follow-up, please.
Yeah.
No problem with follow-ups. With the issues we've had in the last year, filtration is a big concern. Granted, the ventilation air is filtered. Is there filter for the room-induced air?
The room-induced air is not filtered. These are pressure systems. What these systems have the ability to do is deliver an enormous amount of outside air to the space. So for instance, like that 4x4 unit I showed everybody earlier has the ability to go in and deliver a lot of outside air, from 143 CFM each to 475. So no, we don't have extra filtration because it is a pressure system and you would kill the velocity of the air and really reduce your capacity. But we do have the ability to deliver a lot of outside air and thoroughly mix the space. And those are some of the CDC requirements that, I've been looking at. It's where they say, where possible, increase outside air and thoroughly mix. And of course, at the air handler, they want, HEPA filters if possible.
Okay. Do you have secondary condensate connections?
We do not. We could if that was required for a specific job, but we meet that UL 508 requirement for a secondary drain pan with this float switch, which we love. I think we've sold more of these in Rector Seal's history than any other company. And it's because we sold the condensate sensors at one time, years and years ago, and they had a very high failure rate. We got away from them, and we really like these because they go right on the drain pan, 3/4 inch NPT connector. They're simple, they're slightly adjustable, and they do not fail. And they don't require control points, so we like those. A fifth the cost of a condensate sensor.
Can you review some control strategies?
Control strategies. I would have to really defer to some of our control people at the company for that, but I'd be happy to continue the conversation, through email or, correspond through you, Buck.
Okay.
I guess I'll follow up on that one. If somebody can just email me for the control strategies, are you asking about the DOAS system or the pumping system, or the piping system, or the air system in the space? So if this is Jim O'Donnell, if somebody could email me a little more detail, I can respond to that question.
Okay. Control as in modulating flow.
I rarely see modulating air dampers or modulating water valves on these jobs, primarily on the water side, because we're talking about your 1.5 GPM or less generally. So, the question of, is it worth modulating? And on the air side, every now and then we see modulating dampers, except now I see a lot more VAV boxes delivering the air to the beams. That is, in the last 3 years, that maybe 40% of all jobs I see are designed like that now. Now, every now and then, if you have, say, a conference room where you go from 0 people to 30 people in 2 seconds, I see them using maybe a 2-position motorized damper to reduce or minimize the outside air when nobody's in there. But I don't see a lot of modulating, other than in labs. Now, we've done a lot of labs, so yeah, they use modulating dampers and valves in labs.
Okay. For perimeter zones that their cooling loads fluctuate depending on time of year, has a VAV box been attached to a zone or chilled beam to fluctuate airflow? Which you just touched on that.
Yes, they do.
Strictly control valve adjustments to the water flow.
Mm-hmm. I'm sorry, what was the second part of that?
Or is it strictly control valve adjustments for water flow?
No, one of the benefits are you can almost design, anything that makes sense. You're just not locked in the same boxes with a sensible only design. So, if you can do it with other devices, I would say yes.
Okay. Well, that, if anybody else has any more questions, please feel free to pop them in. We still have about 20 minutes yet. We're going to have, Bob would like to show you the selection program, if you'd like to stick around, and maybe a couple pictures of some installations. So
sure, and I'll get right to the heart of this right here. This is just an Excel-based selection program. It has an algorithm in the background with a coil selection program. So it's 1 megabyte. It could be sent back and forth through email effortlessly. And what we do is usually get a round of discussion going with engineers. So if somebody sends load sheets and I have room names and unit IDs, great. I'll put all those in advance. Square foot, so we can calculate CFM per square foot. So the more information we have, the more we can input. So, but what we can do with no information is I can click the, oh, you know what? This is the wrong selection program. What am I doing here? I apologize. One moment. All right, it looks the same. I apologize for the malfunction here. There, luckily nobody can see me sweating bullets. All right, same program, same look, the actual correct one this time. So this is the new climate selection program. In advance, we go in and we set up the water temperature. So if you're going to use 45-degree water, say 45-degree water, or you could put 58-degree water in there, whatever you want, 120. So we'll go 140 on the entering water for heating into the coil, so top end of a condensing boiler. So now we would set up our primary air conditions that we're going to deliver to this unit. So, obviously, if it's a sensible only design, we're going to be, somewhere closer to 55 or under on the outside air and at lower grain. So if this was sensible only, we would probably be at 55, let's see, at 50. So 55, 50, if you swing out to the right here we have primary grains of moisture per pound in the air, and it's automatically calculated when you input the primary air. It's just going to show you right there as a reference. So that's pretty common right there, what we would see for a sensible only design. So since we are going to use cold water, we'll say use 60-degree water at, let's see, 55 grains, which is about 56, 57 grains of moisture per pound in the air. Primary air for heating, we'll leave right at 60 degrees. So we go over here, if we had an altitude, we would put it there. I believe, Harrisburg right here at about 300 feet. So are we in Syracuse. So I'm not going to put anything there. Our return conditions, 75-64. So obviously this is a 55 RH design. If we put 62.5, then we would be, trying to hold it to 50% RH. So I'll leave it at 75-64 because that's one of the advantages you have if you're going to use cold water. You're not forced to design at 50% RH. So now that we have that set up, we have the air handler set up, we have the return conditions set up, we could say, hey, is there glycol in the system? Because if there is, we better put it in. So we could go over here, we could put polypropylene glycol in there and then what percentage it is right there. So it obviously takes into account the reduction in capacity. Once all that is set up, we can go over and we could select the unit. Since I went and messed with that, they wants me to play with that. Okay, so that is 0. Let's leave that 0. So a Q360, that's 10% water, doesn't matter. Q360, that's the 4x4 all-way blow I was showing you. This really is a workhorse. This is the unit that you can put 2 of these in a 1,000-square-foot classroom, deliver an enormous amount of air at a very low static pressure. So I'll show you real quick. It's high and low, like I mentioned, 0.2 inches of static. Our smallest nozzle, so there's 3 nozzle sizes, small, medium, and large. I'll calculate to see where we're at 0.2 inches of static pressure, 143 CFM of air being delivered to that inlet right there under those conditions. This happens to be at an NC14 sound level. And of course, we have ETL that backs that up, third-party testing that backs up the sound throws and capacity for this equipment. So it's not just us saying it. We've incorporated that exact data right into this selection program. And you would measure that static pressure at the exact same place. ETL would measure that static pressure. So on the low end, it's 143, and on the high end, biggest nozzle at the highest static pressure, 476 CFM of outside air. You'll notice about 3-to-1 induction rate. So the total air movement in the space is the outside air being delivered and the recirculation that's occurring through the coil. So that is our total air movement. Now, of course, we don't have correct CFM per square foot because we don't have any CFM or square foot in there. So that's 1.29 CFM per square foot in a 1,000 square foot classroom, but we wouldn't use one unit in there. So since we were saying it's a classroom, or I'm saying it's a classroom, I'm going to go ahead and calculate 2 units in there. That's way too much outside air. So to save a little time, I know we're going to have to be with about the medium-sized nozzle at, say, 0.4 if we're going to hit about, what for a classroom, at 450 CFM of outside, 450 CFM of outside air. Now, I'm putting that there just as a reference, so I know what I have to hit right here. So 484, we're getting closer. I know that I can just drop the static pressure again and get pretty close. So now we're at 459. So our NC sound rating is at an NC 17. We have an 8-foot throw in every direction off this unit. This is has a 360-degree spiral coil in there. So we are throwing in every direction. That's how we're able to go in a 1,000 square foot classroom with 2 units. Okay, so say we like that selection, we just add that to our schedule. And our schedule, we give you more information than the average chilled beam manufacturer because other manufacturers don't deal with the latent capacity. So they let the engineer worry about the latent in their primary air, and they don't want to talk about it even. But we're going to show you, obviously because we're a condensing system, we're going to show you under these conditions just how much condensation we're producing. So for those 2 4x4 units, we're producing, 0.4 gallons an hour. So, that's kind of what I'm talking about is the almost absurdity to some of these designs to avoid small amounts of water in each space.
Is that throw at 150 feet per minute?
I believe it's at 100 feet per minute. Yeah, right there. And I have all that ETL data that we hand out with submittals, or if engineers want to see that in advance. So most importantly, obviously, we have a target here that we want to hit. So you can input, what your target is that you're trying to hit. And so really hitting the total isn't as important as, hitting your total sensible and your total latent. So really we use that for total sensible. So we know that when we've met capacity. So we're going to give you entering water, leaving water. We're going to show you, like in this case right here, she's almost a 20-degree delta T under this scenario. So we just really have more tools to offer engineers than the average chilled beam company that says this is how you must design. So we have a lot of different pieces of equipment too. So that is an all-way blow unit. We have Soffit units. This is a very, very popular unit now. Again, has enormous capacity from very low. So at 0.2 inches of static with the smallest nozzles and only 1 row of them, as low as 38 CFM in that space with about, about a 4.5 to 1 induction rate. Or we go to our biggest nozzle with 2 rows. And again, at an inch of static, it goes from 38 to 368 CFM of outside air. So enormous capacity.
Is the throw isothermal?
I would have to look and see if that is the case. I do not believe so.
Okay.
Okay, so that would be a Soffit unit. And again, on our selection program, we show you its CFM ranges, its size. So you always have that information. So an AIB, high static. Okay, let's choose an ACB. So say we choose an ACB and we want to calculate what it's going to do here. Possible condensation. There are sensible only units. Please check design conditions. So what we're going to do with a sensible only device is we're going to keep everybody out of trouble. Early on, we had engineers using that, and we do have some sensible only units. I guess what I would say is we're polar opposites of every other manufacturer. 95% of all of our models have drain pans that meet code. 5% don't because they're sensible only. And our competition is, again, the polar opposite. So they're 95% of their units don't have drain pans, and a few do now, so they can compete. So this is an ACB. We're going to go to an AIB, which is just an active induction beam with a drain pan, can handle 45-degree water, has a much higher induction rate, you'll notice, total air. So higher induction rate is good in some scenarios. In other scenarios, it can add to maybe a high CFM per square foot in a space. Where they're really beneficial is if you have a corner office with a big solar load, but only 15, 20 CFM outside air requirement. Higher induction rate is your friend in that scenario because you're going to get more capacity from that coil with less outside air. So that is our selection program. I promise if somebody played around with this for 10 minutes, you'll really start to understand the relationship between static pressure, sound, in performance. It becomes very clear, where the point of diminishing returns are on your GPMs. You can see exactly where the drop off is. And it's really, it becomes intuitive, the program with the equipment. And you'll get a better understanding for not just our equipment, but how induction units and chilled beams work in general. I did want to show a few pictures of some jobs. We are proud of a lot of our jobs, very, very nice jobs. Oh, sorry about that. Okay, so University of Buffalo, we do a lot of university work. They have linear units in the ceilings. When we do advocate for multi-fin diffusers, when possible, they perform better. When you CFD model it, you can really see the performance difference compared to a single slot diffuser that's just shooting that air across the ceiling line. All-way blow 2x2. This is a teaching university. It's not actually, obviously, an operating theater. This equipment would not be appropriate for that. But in universities, they certainly are. Hospital patient rooms, certainly appropriate. We have a lot of jobs in hospitals. Currently, I think I'm working on 5 VA hospital jobs. Most of the time now, they're using 2 one-way blow units in this kind of configuration because they would like to direct the breath or the exhaust off the patient to the exhaust in the building. So they have design strategies, usually where they are set up the units perpendicularly. For instance, this is the same space. You have a unit blowing in the patient bed over here, and the other unit in the room, when you walk in, you're looking right here, it's blowing kind of towards over the patient. So they do have those in a perpendicular manner.
Bob, we have one more question that popped up here.
Yes, sir.
When trying to select beams for a job, it seems like there are many levers to pull. Do you have a recommendation for default parameters when selecting?
Now, are we talking about unit selection itself or setting up the air handler and the water conditions? I mean, are we looking for what would be a good default design?
No, it's Bob. It's what on the when you were going through the selection program, there were a lot of tabs. So Stephen is asking, are there any default selections that you would recommend starting with?
When you say tabs, what do you mean tabs? Like for here?
Yeah, on the bottom portion. Yes, exactly. Like when you have 3 different nozzles, what would be maybe a shortcut to protect, select, is it best to select the largest nozzle because that gets you the more bang for your buck? I think that's what Stephen is asking about.
That's a great question because there's so much nuance to it. And it really depends on what the goal is. I've had some engineers say, hey, we're designing everything at 0.4 inches of static. So I work within those parameters. Now, if it were up to me based on what I know or what I've seen, I guess, I would say normally what we do when we're going to make a selection is because overventilating is a no-no, generally speaking, and has been and probably will continue to be. So what I do is when I'm about to make a selection, I choose the unit. I look at how much outside air I need. Generally speaking, you're going to have an idea if you play with this thing for 10 or 15 minutes. And I would say to myself, is sound important? Is low static pressure important? I would ask myself that, and then I would always start with the highest GPM and the lowest static pressure. So my strategy when I design, unless told differently, is to only deliver the outside air required. So by maxing out the GPM first, I can then find out how much outside air I need to meet these loads. And when I do, then I trim back the GPM. Does that answer your question? Oh, as far as choosing a nozzle size, I would say it will be pretty evident. The goal would be to, if you don't have to use the 38 nozzle, I would say, well, it has its advantages. I can't say that. So, you know how I said earlier when I had to meet that 450 CFM of outside air, and I did it with the medium nozzle. I could also hit that with the largest nozzle at a very low static pressure. So it may be more important for this particular job to show an NC 16 here than it would be something higher. So using a bigger nozzle will deliver more air at a lower static pressure. So it's really, there depends on how the engineer wants to design it. But yes, you know, there's crossover between nozzles. So you can hit that same CFM range with two different nozzles, one at a higher static, one at a very lower static. That answer your question?
I'm guessing he hasn't responded yet.
Okay.
So
really lower static, smaller nozzle, and just always being cognizant of what's important. Sound, static pressure. I usually know those things, or early on I make assumptions. If an engineer gives me load sheets, I go in and make some assumptions. Hey, we're going to try to keep this quiet. We're going to try to use lower static pressures and obviously trim back the GPMs once I hit those loads.
great. Awesome. I don't think we have any more questions, and we are right at time.
Really?
Yes, sir.
Right.
So went pretty fast.
Yes, it did. Well, hopefully I've met the objective, and, you know, we made a direct comparison, and, you know, I didn't beat up too much on sensible only beams because we do have plenty of projects that are sensible only. Both systems work fine. Induction beam systems generally tend to be come in lower cost. You need less equipment, less complicated dedicated outside air handlers. So it is a less complicated system using gravity draining versus you know, custom air handler. And I'm happy to further any conversation in the future. Generally, if an engineer has a project, they don't know whether they even want to go in this direction or whether it's viable. They could just send, you know, Buck or Jim or Gina or someone some load sheets or some drawings, and I could easily come up with some selections and a budget and kind of give you a global look at it with this product. Because this selection program is also good for saying, hey, let's look at this globally. Got 1 million BTU requirement in this space. How many units is it going to take to hit it? So we're at 24,000 right there. What am I going to need? 25 units. Okay, so we see where we're at there. We max out the GPM there on the cooling. Okay, so maybe it's going to take 75 units throughout the building to hit that. So it turns green, so we hit that. So we just have the ability now to kind of look at that globally, and it has some value. You know, we could certainly, you know, kind of surmise chiller size and some other pretty good information. how much outside air would you need to do that? So in this case, what are we using? 7,800 CFM of outside air in that scenario. So it really does have a lot of value other than just making selections for individual selections.
Sure. And we're here as a resource for you, for you all who joined us today. So please reach out to your sales guy. If you don't have one, hit myself up or reach out to Jim O'Donnell. Again, we're here as a resource, and we greatly appreciate you taking the time out of your day to spend some time with us. And again, I'd like to thank Bob for joining us. And next month's webinar is, Jim?
That's on Tuesday, June 22nd. Once again at lunchtime, we'll do a webinar as before. I'm going to be the presenter. It's going to be on dedicated outside air systems. We're going to talk about the psychometrics of them. We're going to call it part one. Part one's going to focus on kind of refrigeration based DOAS units, and then part two is going to deal with requirements for lower dew point and dry bulb temperatures, where you normally have to incorporate a passive or active desiccant dehumidifier to get your air that low. So that's what we're going to do. We'll have the part one in June, and then we'll take off the summer and ramp up again come the fall in September.
Great. Well, again, thank you, everybody. Bob, thank you.
Thank you for listening.
Thank you, Bob. Great job.
Appreciate it. Thank you.
Great to have you. And we'll see you all next time. Thanks, everyone.
Bye-bye.